All right, guys and gals, today we're going to venture out into our third unit. It's going to be right triangles, so we'll be in chapter 7. It's one of our shorter units, but many people find it's also one of the more difficult. The first few sections are fairly straightforward, and then towards the end, the difficulty kind of ramps up. So this first part should be review. If not, hopefully you'll learn it very quickly. It's what we call the Pythagorean theorem. The Pythagorean theorem deals with right triangles. The root of Pythagorean is an individual's name, Pythagoras. Pythagoras was a Greek that lived a number of years ago on the island of Samos. He's the one who ultimately is given credit for this theorem. Never mind that we've got records that would indicate perhaps the Babylonians or ancient Egyptians also had knowledge of it. But that's neither here nor there. Let's get into it. First, before we get into the actual theorem itself, let's talk about parts of a right triangle, just to make certain that we're all clear on that. When we're talking about a right triangle, obviously we have our right angle here. The side opposite that right angle is given a fun name. It is called the hypotenuse. And it's spelled just like it sounds, hypotenuse. And it's basically Greek for longest side, or at least that's what I say. The other two sides of our triangle are referred to as legs. So we've got a leg here and we've got a leg there. Typically, when we're naming sides and angles, if this is angle A, for example, then the side opposite it would be side A, and so on and so forth. So angle B was side B, and so on. Sides A and B, as I mentioned, are legs. C, of course, is the hypotenuse. And it's this sort of setup that gets us ready for the Pythagorean theorem, which is as follows. The Pythagorean theorem deals with the lengths of the sides of a right triangle. And here's what it says. In a right triangle, so that's our given, if we know that we have a right triangle, the sum of the squares of the measures of the legs is equal to the square of the measure of the hypotenuse. In other words, if I take side A and square it, and take side B, whatever that distance is, and square it, and add those together, whatever I get is going to be the same as C squared. For example, let's say that A was 3 and B was 4. We could then use this to figure out, well, what is that hypotenuse measure? So if I take 3 squared, that's 9, and 4 squared, that's 16, that would let me know what C squared would be. So 9 and 16, of course, make 25. And of course, I don't want to know what C squared is. I just want to know what C is. So I'll have to take a square root. And in this case, C is 5. So this distance here would be 5 units, whether we're talking inches, miles, whatever, it doesn't matter. So we can use the Pythagorean theorem to find missing sides. Okay. Also, the Pythagorean theorem is another way of talking about our distance formula. Our distance formula on the coordinate grid is based on the Pythagorean theorem. For example, if I have a point here and a point here, the distance formula that we've been using all year basically creates a right triangle. We find the distance, or the difference rather, in the x's, the difference in the y's, and that allows us to find that dotted distance. So the distance formula is just a regurgitation of Pythagoras' theorem, just put a slightly different way. So onward and upward. Here's my favorite proof of the theorem, all right? It was developed in India many, many years ago, and the mathematician that developed it simply had one word to describe his work, and that is behold. So take a look. Here's that right triangle again. If this is side A, and this is side B, and this is side C, notice what you can do. Here we have A squared. Notice it's A by A. Here we've got B squared, side B and side B, so this is B squared. And notice between the two figures, all they've done is rearrange it so that instead of these triangles forming rectangles with two squares, all of the triangles have simply been moved to the edge, leaving a larger square in the center. In this case, notice we've got side C, so here is side C again. And notice this is C by C, or C squared. So A squared added to B squared is the same as C squared. Notice these overall squares are the same size. They have the same number of triangles within. So this orange space, of course, is the same in both. This is just one of many potential proofs for the theorem. I like this one simply for its simplicity. One word, behold, and there it is. Okay, let's keep going. Some quick exercises. Let's see if we can use this. For example, we've got a couple of triangles here. We know that this one here on the right is a right triangle. If this whole distance is 14, notice we've got equal distance here. This must be a perpendicular bisector. So if this is 14, then this is 7. So again, if I take x squared, add it to 7 squared, that should get me 8 squared. Well, that, of course, is 49 and 64. Of course, we don't know what x squared is yet. We're still working on that. All we've got to do then is take 49 away from 64, and that'll get us what our x squared number would be. Remember, we don't want just x squared, right? That's not our purpose. Our purpose is not to say that x squared in this case is 15. We couldn't care less. What we want to know is what x is worth. What I find is a lot of students will stop at this step and not make that last jump. So in this case, taking a square, let's talk about square roots real quick. 15 is not a perfect square number, so one way to end our result is like this, to say that it's just the square root of 15. Cool, we're done. Other numbers, for example, let's pretend that our number was 12. So let's say we ended up with the square root of 12. All right. This square root of 15 would be a perfectly valid answer. Obviously, we could type that into a calculator and get the square root of 15 as being just a little bit short of 4. In this case, it's roughly, say, 3.87. All right, thereabouts. However, if we've got a number like this, say the square root of 12, the square root of 12 is not a simplified version. We can simplify it further. I know that 12 is made up of 3 times 4. Notice 4 is a perfect square number. The square root of 4 is, of course, 2, and the 3 is not perfect, so we would simply leave it behind. So the square root of 12 is equal to 2 radical 3. This is an exact answer. If I were to type in square root of 12 and get a decimal, that would be an approximate answer. So if we do have square roots, we do need to try to simplify them if at all possible. All right, so just heads up there. Let's try another one. So in this case, I would have 4 squared added to x squared is 8 squared. So in this case, 16, and of course, we don't know what x is yet, and 64. Again, we don't want just x squared. A lot of people, for whatever reason, want to stop at this step. I don't know why. Please don't do that. Okay, don't stop here. Keep going. We need to go ahead and take that square root of both sides. And in this case, very, very, very close to 7. 6.9, we'll call it 6.93 approximately. And again, if we wanted to simplify the square root of 48, well, then we would need to find, well, what numbers could we break 48 into? For example, I could take 48 and divide it by 4. 4 is a nice perfect number. 12 is not a perfect square, that is. I could break that down again to 4 and 3. Well, the square root of 4 is 2. The square root of 4 is 2. 2 times 2 is 4. And then, of course, 3 is not perfect, so we would leave it behind. So I could say 6.93, or roughly 4 times, that's roughly 4 times radical 3. And that would be an acceptable answer. This being rounded and then this being simplified. All right, let's try one more. We've got 20 this time, and 28 is equal to x squared. So if I square 20 and add it to 28 squared, we get 1100, what was that, 84? Goodness, that's a big one. And again, we don't want to stay here. We don't care about x squared. We want to know what x is. So we'll need to take that square root. And in this case, I'm going to go ahead and leave it as a decimal, roughly 34 and change. Yeah, we'll make sure we write approximately 34.4. In this case, I'm not going to bother to try to simplify that one down. But again, just be aware you can do it either way. And make sure you pay attention to what the directions are. If it doesn't say anything, then you could round, say, to the tens position. If it does get specific, though, again, make certain that you round appropriately, whatever that might be. Okay. Let's take a look at the converse. Remember, a converse is when we take something and put it in the reverse order. So conversely, the converse of the Pythagorean theorem says, look, if the sum of the squares of the measures of the two sides equals the square of the measure of the longest, then the triangle is right. In other words, this is a test for right triangles. right? That's what we can do with this. So, for example, let's pretend that instead of knowing that it's a right triangle, let's say we had sides, and I'm going to make this up here. How about something like 5, 12, and 13? All right. Is this a right triangle? All right. Well, to test it, we could simply take 5 squared plus 12 squared. And remember, the longest side is what the other end has to be, so 13 squared. And we can use this to see if the two sides are equal, then cool, it's a right triangle. If they're not equal, well, then cool, it's not. Let's work it out. So we'd get 25, what is that? 144, and what is that? 169. Let's add those together, 169. So yeah, it works. In this case, we've got a right triangle, all right? But what happens if, let's say, it doesn't equal, all right? So let's talk about that. If it's right, let's make a note here. If it's right, then a squared plus b squared is c squared. All right, so we got that much down. But what if it's not right? All right, what if we end up that the two sides aren't equal? What does that mean? Well, there are only two other options for triangles. We could have something that's acute, or we could have something that is obtuse. We would have an acute triangle if a squared added to b squared is greater than c squared. All right, so if the AB side ends up being greater, then we've got an acute triangle. If, however, that C side ends up being the larger, then it's obtuse. So very quickly, we can determine with the Pythagorean theorem what sort of triangle are we dealing with. If it's equal, of course, then it's a right triangle. If the AB side's greater, it's acute. If the C side is greater, then we're dealing with something that's obtuse. So it should be very quick and easy for us to determine what are we dealing with. All right. Let's try some. So for example, we can try and figure out if we have a right triangle for these situations. So what I would need to do is find the distance for each side. So what does the distance say for QR? What's the distance say for RS? And then what's the distance say for QS? So let's see what we can find. From Q to R, distance of 1 there, so that would cancel out. 0 to 6, well, that would be a distance of 6 then. In this case, it would run up and down. All right, let's try the next one. Here we go. From 1 to 9, well, that's a distance of 8. From 6 to 0, that's a distance of 6. So 8 squared plus 6 squared is c squared. Remember, the distance formula is basically the Pythagorean theorem just rewritten. So we've got 64, we've got 36, and of course that would be c squared. Add those together, that's 100. Which means C, I'm doing my work kind of upside down and backwards there. But basically, we got a side of 10. Cool. And then our last one from Q to S, let's see, we have a difference of 8. Excellent. So if I look at those, well, geez, isn't that familiar? 6, 8, 10. 6, 8, 10. So yeah, very much a right triangle. It works within the Pythagorean theorem. Cool. All right. Let's try another one. We've got to determine whether each set of numbers can be the measures of the sides of a right triangle, and then if they perform what we call a Pythagorean triple. A Pythagorean triple is 3 whole numbers that would work in the Pythagorean theorem. So obviously 8, 6, and 10 would be a Pythagorean triple, all whole, and we do get a right triangle. Let's try this one. So if I have 8 squared plus 15 squared, does that equal 17 squared? All right. Well, let's work through that real quick. So 8 squared added to 15 squared, that is 289. And then if we take 17 and square it, what do you know? 289. So not only is this a right triangle, so it is right. 8, 15, and 17 are what are called Pythagorean triples. All 3 numbers will work in the Pythagorean theorem. Some more common Pythagorean triples that you'll need to know. 7, 24, 25 is another triple. The most common that you'll see is 3, 4, 5. All right, that's a very well-known triple, one that you definitely want to commit to memory. Another one that we've seen today is 5, 12, 13. That's another very common triple. These would be the 2 that I would commit to memory. There are others, obviously. As a matter of fact, there's an infinite number of triples, but I would definitely commit those 2 to memory. Those will be ones that you'll see pretty much now and forevermore in your mathematical career. So, Pythagorean theorem, not a very difficult concept. Hopefully it's one that you've seen before now. If you've got questions, please bring them to class. Otherwise, have a good day.